Hello there, astronomers and astronomites. We are going to talk about the spectrum of light. We talked a little bit today about the evolution of the human eye, and actually the eye on planet Earth, and how it is just an exquisite piece of biological technology that's helped us become the master of our domains and help us look beyond Earth to the stars. But how well do our eyes actually serve us for looking into the depths of space? Well, we're going to learn about that today. Okay, so here's a planet, Kepler 438b. We're going to talk a little bit more about this. We're going to talk about why it is of interest, what things we look for to know whether something is of interest to us or not. Because obviously, as you might already know, some of these things that we look at are incredibly far and unfathomably far by human standards. So what is it that we look at that would let us know, like, oh, this is something that's of interest to us? Okay, well, as we said today, about 90% of our our sensory neurons are connected to our eyes, and that's because we are surrounded by light information. So it makes sense that our ancestors would have developed a keen sense of sight, so that way we can absorb as much information as possible. You know, whether that was to help us survive by evading or going towards light, or, you know, being able to perceive light information off of a incoming predator or perhaps migratory prey. Being able to see is an evolutionary advantage. So, a couple things about light. The speed of light is 3 times 10 to the 8th meters per second. So if you've taken regular physics, you probably know that. That's 3, oh, that's ugly. 3 times 10 to the 8th meters per second, or 3 million meters per second. Okay, that means it can travel around the Earth 7 times in 1 second. Nothing by convention is faster than the speed of light, except if you want to get really technical and talk about the space, expansion of space is expanding faster than the speed of light, and that's why we have this thing called a photon horizon. It is a point in which we can't see beyond because the space at those regions is expanding at a rate faster than light can travel. But if you were in that space where it's expanding, relativistically speaking, the speed of light would still be 3 times 10 to the 8th meters per second. It's kind of weird how that works. Light is a transverse wave, so when you think transverse, you should think of like a transverse flute. So if you're looking at a flute, right, you don't blow into a flute this way, right? Okay. That would be parallel, right? Well, what you do, though, is here's your head right here. There's a hole right here, and you blow this way. And as you blow straight down, this is a right angle. Right angles mean transverse. This equals transverse. Okay, right angle means transverse. Okay, so a right angle means, in the context of waves, it's traveling like this. That means the energy of the wave is traveling this way, whereas the medium itself is oscillating this way. It's moving back and forth this way. So the medium is not being displaced permanently, the energy is, and these energy to wave angle is a right angle to each other. You can kind of think about it like this. This almost looks like it says the word transverse, right? And that's how you can remember it. Easy peasy. Okay. So even though the speed of light is unimaginably fast, it still takes hours to reach distant solar systems and planets, years to reach the nearest stars, and millions or billions of years to reach distant galaxies. If I were to send a message to Mars, this isn't really even an if, this is what it actually is. And I'm going to actually draw these about the right sizes. Here's Earth, about a third larger than its sister planet Mars. Actually, Venus is closer to being our sister planet. It actually has an atmosphere and it's closer in size to us. But anyways, if I were to send a message to the Mars rover, all the way over here, or one of the many Mars rovers actually, there are lots of them over there. If I were to send something to the Mars rover, here he is right here, Mr. Mars rover. Okay, and I were to send something this way. To get a message back from them, radio waves would take 12 minutes each direction. So it would take 12 minutes this way and 12 minutes this way. And that's keeping in mind that each direction we're traveling at 3 million meters per second. So that's a meter stick, 3 million of those, 3 million meter sticks per second that light's traveling. And it would still take 24 minutes for us to get confirmation that if we told the Mars rover to move over a little bit, that it actually did so, and that it was still actually alive. What's even more astounding is that if I were to turn off the sun, turn that frickin' thing off, I'm trying to sleep, right? If I were to, or the sun were to suddenly just go out, right? For the Earth to know that the sun was actually gone would take 8 minutes. So even if the sun were to completely go away, the last ray of light wouldn't reach Earth for a full 8 minutes. So that's how far away the sun is. Very, very far. About 93 million miles away. Or 1.46 million kilometers. Okay, so this is an incredibly, inconceivably far distance. It would take 8 minutes. Oddly enough, too, gravity would take it. We would still feel the sun's gravity for a full 8 minutes after we're gone. Gravity also travels at 3 times 10 to the 8th meters per second. Okay, so here's the electromagnetic spectrum. Human beings are excellent at seeing these colors right here. We're incredibly gifted at seeing Roy G. Biv, right? But it's worth noting that Roy G. Biv, this picture right here is actually a little bit misleading. If radio waves, microwaves, infrared radiation, visible light, ultraviolet, and X-ray, and gamma rays are the gamut of all electromagnetic radiation, I'm going to call it EM, the EM spectrum. Visible light is actually not anywhere near this percentage of this entire spectrum right here. Visible light is actually, if I were to draw like a little bar right here, if this were all the different forms of electromagnetic radiation, visible light would only be this very narrow band. This would be visible light. The rest of this stuff right here is not visible. At least not to the human eye. Okay, the electromagnetic spectrum is a continuous spectrum, which means even though there are these little separations right here and here, these little gaps, it's not easily distinguishable from one thing to the next. That's what we call a continuum. Okay, it's a spectrum. It's a continuous spectrum. Okay, and let's look at the relationships as we go down the line here. Let's get rid of all this junk. Okay, when we're looking at wavelength, which is this upside down y, lambda, wavelength. Wavelength goes from really long to really, really, really short as we go this way. Okay, we talk about energy. I'm going to make that yellow. We have small energy here at radio waves to very large energy at gamma waves. So you can see that the bigger the wavelength, we have small energy, lower energy. Okay, let's look at frequency. So what does frequency mean? Frequency means how often a wave is propagated, how often a complete wave is formed. So if I say that my wave is from crest to crest, right? So crest is like the top of a mountain. This would be a crest, that would be a crest. So this right here is a wavelength. Or trough to trough is also a wavelength too. This is also a wavelength. I could also make another wave that happens more frequently. So even though the wavelength is small, the frequency is higher. So that means it happens more often. So frequency is this red right here. If I have a high frequency, that means my wavelength must be very small. Okay, these are inversely related, inversely proportional. Okay. an easy way to remember the order of the electromagnetic spectrum from lowest energy to highest energy, from lowest energy radio waves to highest energy gamma waves, or longest wavelength to shortest wavelength, is by remembering this acronym. Red Martians invade Venus using X-ray guns. Learned that from a good physics teacher there at Warren High School, actually. So just remember that. Red for radio, Martians invade. Might have to actually shrink this a little bit. Venus using X-ray guns. Cool or what? Another way to remember this is to memorize this song that I'm probably going to have you sing for a grade. Let's listen to it now. You might not be able to see it, but you can definitely hear it, and you'll never forget it. Okay, so yeah, memorize that, and it'll be a grade. You sing it for extra credit. Or sing it, I don't know. Maybe I'm feeling generous, maybe I'm not. Maybe I'll make you sing it for real. Or you can just remember that red Martians invade Venus using X-ray guns. And just remember that's the order of things. All right. So you also have to know the duality of light as both a particle and a wave. So you can see, just like if I were to yell down a hallway, other people besides the intended recipient of that sound wave would be able to hear it. In other words, if I yell at you, people outside the classroom can hear it. That's because sound travels like a wave in all different directions. It propagates in different directions. Light, similarly, if I shine a light, it bends around corners and things like that. So it's wave-like in that respect. At the same time, we know it has to be a particle because it has physical effects when it comes in contact with things. Very, very small and minuscule, but they're there. I can hit a light sail, something that's really, really thin, has really, really small inertia, and can actually get it to move if I hit it. You also know that light is a particle because it interacts with things like electrons, right? Yeah. Down here are some of the nice phenomena that light can do. We have this thing called the Doppler effect. You certainly have heard this if you've ever heard an ambulance going towards you. As it's going towards you, that woo, woo, woo becomes woo, woo, woo. And as it goes past you, it goes woo, 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 because the sound waves are traveling slower to your ear after it passes you, and faster towards your ear as it's going towards you. It makes sense, right? If you are standing on top of a car, you are going the speed of the car, and then if you were to jump forward off the car, or throw a baseball or something in your hand forward with the car, it would have to be traveling the speed of the car plus whatever speed you added to it. Sound waves will do kind of the same thing. When sound hits your ear, so I'm going to draw like a little red ear right here. It's kind of crusty, whatever. Okay. So remember, in sound, if you have a high frequency, that's a higher pitch. High frequency equals higher pitch. Like oh versus oh. So the difference between those two things is that the oh was a lower pitch, lower frequency, and the oh was a higher pitch or higher frequency. Okay, so what does that look like for your ear? Well, when I did the oh, that means less waves per second were hitting your ear. So here's a wavelength. Here's a wavelength. But when I move towards your ear, what ends up happening is I'm bringing those waves to your ear at a higher rate. The frequency is higher. So when I have a higher frequency, what is that? What does my ear imagine is happening? It imagines that it's hearing a higher pitch. Okay? It's worth noting that regardless of what color light or what color wavelength we have, the speed of the wave without any sort of moving sound source is going to be the same speed. Okay, so what is the application of this in astronomy? Well, when we look at things like visible light, we can see that it looks either a little bit more red or a little bit more blue, red shifted and blue shifted, depending on which part, depending on if it's moving towards us or away from us. Okay, one of the biggest implications for cosmology, the evolution and shape of the universe, is that everything seems to be expanding away from us, seems to be spreading away from us, at least at the farthest distances. And that helps us kind of determine the shape of the universe. Okay, here's some nice pictures of like the sun. Okay, we use light to kind of tell us things. Certainly you've seen rainbows created from like light refracting through windows and things like that. We can actually use prisms to kind of help us understand the composition of stars and the composition of other celestial bodies. We use this thing called the absorption spectrum and the emission spectrum. Okay, the emission and absorption spectrum works off of the Bohr model, which you probably learned about in chemistry. You had to know. So Bohr model. Okay, and the Bohr model is also kind of colloquially known as the planetary model, which is, I guess, apt for what we are studying right now, the planetary model. Okay, the planetary model or the Bohr model. And that's the picture of the atom that looks kind of like this, right? With all this jazz, right? So this is the planetary model. Bohr kind of thought it looked more like this, though. Just like concentric little orbits and stuff like that. And these were called quanta. The separations and distances of energy from here to here were very specific. If this right here was a fixed distance from the nucleus, it meant that I could only add or subtract a very specific amount of energy. Okay, a very specific amount of energy. That's kind of ugly. I'll write that a little better. Okay, these atoms can only absorb or emit or release a certain amount of energy. And it's kind of like walking up a staircase. I can't walk up half a step. I can either go the full step or I can go no step, but I can't walk down or up a partial step. Similarly, atoms are the same. Different types of atoms will only be able to give off or absorb certain colors of light. So hopefully you can kind of see the application already. If certain atoms and elements and compounds emit certain spectra, that means if we look at stars, if we look at planets, and we observe the emission and absorption spectrum, we can tell what they're made out of, and that'll help us. So even though we may never be able to reach these planets, even with satellites, the light travels very, very quickly and tells us a lot of information. Okay, this is kind of what we were talking about earlier. When electrons jump up to higher energy levels, they have to absorb energy. That means they take light away from what we can see. And when they are decreasing their energy level, they're jumping down, they excite electrons. They don't hold those electrons anymore, and they fly off in different colors. Okay, so here's an example. Hydrogen has a very specific absorption and emission spectrum. Every hydrogen atom that is stationary will have this band of colors that you can see when you look through a prism. Helium's different, oxygen's different, water's different. Okay. Now, visible light's all fine and well, but unfortunately there's a lot of stuff in space that occludes or obscures the light. And that's going to be things like dust and things like that. So there's all kinds of dust all over the place. So unfortunately, those dust particles are the wavelength of visible light. So any sort of visible light coming in from the sun, and we're going to go ahead and make that white light, gets absorbed by this dust and stuff, and it doesn't ever make it through. Okay, but luckily for us, there are these other things like radio waves, which are much longer. they don't interact with that dust and they pass straight through. Okay? There are other things too, like ultraviolet. Ultraviolet does not interact with those particles. It's much smaller in wavelength, so it's able to pass straight through. Gamma rays, even smaller than that, they would pass straight through. So ultraviolet and gamma rays would be able to pass through that dust and stuff like that, except there's this thing for ultraviolet called the, say it with me if you know what blocks ultraviolet. It's the ozone layer. So when this ultraviolet comes in right here, it's absorbed by the ozone layer and scatters off and doesn't give us cancer and stuff like that. Some of it gets through, a little bit gets through, but certainly not this really concentrated beam of ultraviolet. It gets scattered by the ozone layer. So you can kind of see why it would be problematic if we put stuff in the atmosphere that punched a hole in it, because then that ultraviolet would not be shielded there and it would get straight through to us. Okay? Now, what about gamma rays? Why aren't we getting hit by gamma rays all the time and our DNA getting all jacked up? Because gamma rays are about the size of our DNA. So they're able to interact with them very, very well and make changes on the fly, which is not good. So you see like X-Men and stuff like that, like, oh yeah, mutations, the Ninja Turtles and stuff, it's great. Mutations, yeah. If I just got bit by a radioactive spider and I mutated, I'd be Spider-Man. Well, you'd be Spider-Man, but you'd be all jacked up and you might have a second head growing out of your neck or something. You might, so you don't want two butts. You just don't want that, especially you wouldn't want like a butt in your elbow or something like that. It'd be crazy. You'd run out of toilet paper so quickly. So you don't want gamma rays, and luckily for us, we have this thing called a magnetosphere. So we have this nice magnetosphere that actually blocks us from way out in outer space. So these gamma rays actually never get to go here. So the magnetosphere comes out of the top of the Earth, blocks us. It's actually the weakest at the North and South Pole. But everywhere else, there's this nice magnetosphere that as these incoming gamma rays come in, they get shot away. Got these positive things getting pushed away by other positively charged things, and we're protected that way. Okay. Now a lot of these things are kind of corralled into the northern section of the globe and the southern section of the globe. And so what ends up happening is they interact with other particles in the air. Ultraviolet does the same thing too. And you end up getting these nice, beautiful lights. These nice, beautiful green lights kind of go all over the place. Greenish blue lights, right? And those are the northern and southern lights. The aurora borealis and the aurora australis. Okay? Different atoms, like we were saying before, are going to emit different wavelengths of light. And we're able to look at other planets and kind of look at the emission spectrum. And if we know that CO2 on Earth kind of gives us this reading, we can look at other planets and go, oh, that's CO2, but not very rich in oxygen and in water or oxygen. Okay, this is how we do astrobiology, right? We look for signs of life by their emission spectra. We can tell if there's cyanobacteria, or we can tell if there's evidence of cyanobacteria, oxygen making chlorophyll organisms, right? Just by looking to see like what is in the atmosphere of these planets. So this is called spectroscopy. Spectroscopy. Spectro is like the spectrum of color, and scopy means to scope or to see it. So seeing the colors, seeing the spectrum, explains the makeup of exoplanets, even though we will probably never get there. Spectral lines are like a star's fingerprint. Okay, when you think spectroscopy, think atomic fingerprint. Since they both can be categorized, are unique, make patterns, and are characterized by the individual that produced them. Spectroscopy of the stars tells us the temperature, age, distance, motion, and composition. So if you're going into astronomy, and you want to go into astronomy, you really need to know your physics, you really need to understand your chemistry. At Southwest Research, they have a machine that literally you put in things like gasoline and fuel, because they want to test the purity of these gasoline and fuel. They'll burn it off and they run it through a mass spectrometer. And the spectrometer will pump out pages and pages and pages of spectroscopic data. And then a chemist will sit there and look at it for hours and hours and hours and determine what type of impurities were in that fuel. So these are things that you can apply. So a lot of astronomers actually don't have necessarily a background in astronomy, but they have backgrounds in hard chemistry and hard physics and mathematics that eventually is called upon by the discipline of astronomy for the purposes of application to looking at the stars and discovering stars. So if you want to be a good astronomer, you don't start out as an astronomer necessarily. You start out as a mathematician, you start out as a chemist, you start out as a physicist, and then those things are brought on board. You are recruited by the discipline for your expertise. Probably one of the most famous X-ray astronomers, he was the first X-ray astronomer, was a man named Walter Lewin. Okay, let me see if I can find a picture of him real quick. Yeah, this guy right here is Walter Lewin. He's one of the famous MIT professors. I think my sister actually got to sit in on a lecture that he had. She went to MIT. She didn't finish, but she did go there. I'm still very proud of her. Okay, if she's listening to this, I'm sorry. But Walter Lewin actually survived the Holocaust. They escaped right before the Nazis came to their town, a little Austrian town. And he actually had this really poignant, really kind of interesting and sad and just kind of haunting story about how he can never wear or touch the fabric wool ever again in his life, because they lived on a sheep farm, and everything they had, no matter what it was, socks, scarves, pillowcases, mittens, just all harsh wool. It's just not refined because it was made by them, and they used what they had. But he says to this day he can't stand the touch of wool to his skin. Just makes him feel sick, and it makes him remember just all the bad things that happened to his family members. So if you're ever interested, look up Walter Lewin on YouTube, watch some of his lectures. He does some really, really cool physics demos with the pendulum and stuff like that, conservation of momentum, conservation of energy, but he's a world-renowned scientist. But what he was most known for in the 60s was his pioneering research in X-ray measurements, so being able to measure natural sources of X-rays. And up until this point, it was just a hypothesis that X-rays were being emitted by the sun and being emitted in outer space. And it sounds kind of crazy because we've been talking about X-rays just kind of as a you take it for granted. You listen to me say that, oh, X-rays are emitted from things in space, and you're just like, oh, okay, yeah, sure, it's a fact now. But it wasn't always known. It just wasn't always known. We didn't know that radio waves came from space as well. And how would we? You can't just believe it because you want to. There was nothing in outer space to measure whether or not X-rays are coming. It's like, well, why couldn't we just measure it from Earth? Well, silly, because of the reasons I told you earlier. We have the ozone layer to block ultraviolet, a lot of the ultraviolet light. We have the magnetosphere to block positrons and gamma rays and things like that. So Walter Lewin was one of the pioneering scientists to help start creating ways to measure X-rays in space. And so he actually was able to measure the wavelength of an X-ray from something as far as 10 light years away or something like that. And his margin of error would be about the width of a dime if it was on its side. If you had a stack of dimes, it'd be the width of one of those dimes. That's pretty damn accurate. So this guy was brought on for his accuracy of measuring radio waves. Oh, I'm sorry, X-rays. And they invented a field of astronomy called X-ray astronomy. They started creating X-ray telescopes based off of Dr. Lewin's pioneering research on X-rays. Pretty cool, right? But he had no idea he was going to be an astronomer, ever. But that's what I mean by, you don't know what your skill is going to be used for. You just got to be good at it. You could be co-opted and recruited for a field you have no idea you even had interest in, right? And you could make a huge contribution. Let that be a lesson to you, whenever you ask yourself, what am I going to use this for? Well, Walter Lewin didn't know what X-rays were going to be used for, but it ended up being probably one of the most important additions to the field of modern astronomy. So try to be like that too. Maybe you don't know what it is you're taking a chemistry class for. Maybe you don't know why you're taking a U.S. history course. But just give it a chance. Be patient with yourself. It could be very important. Okay, and here's the table of elements if we were to look at it as a table of emission spectra. So you can see that all these are very unique, very tediously different. But to somebody who studies this for years and years and years, some of these become a little bit more distinguishable over time. But now you know what this means. When I point a telescope to the sky and I put a little prism in front of the telescope, obviously it's a bit more complex than doing something like that, but the concept is the same. I can actually start separating out the light by the elements that are producing those lights. Okay, so what do I need to know? You should be able to answer these questions on your own. I would go ahead and do that on your own paper. You're probably going to have a quiz over this soon. What is the speed of light? Light is both a blink and a blink. How are energy and wavelength related? Blue light has a high or low frequency. When an object is blue shifting, what is it doing? How does an electron jump up? When an electron jumps up or down, it blank a specific color of light. Different atoms emit what? What do spectroscopes do? Besides temperature and composition, what else does spectroscopy tell us about stars? All right, write those down. Ask me, ask your neighbor, ask whoever you want to try to see if you can answer those questions. Thank you. Good luck.